So let's talk about those blunt versus slender bodies. Okay, so blunt versus slender, which is better? When it comes to drag, slender is way better, but we're going to find that that's actually a horrible, horrible thing here when it comes to aerodynamic heating. So if we want, we can go back to our Stanton number to figure out how we're going to differentiate between these two. Okay, so our overall integrated Stanton number, so this is just taking into account the entire body. So let's just call this entire body. Entire. Before it was like 1 point, okay? This is going to be equal to the amount of heat going into my body over time over the rest of the stuff we got kind of used to. So rho infinity times V infinity times H naught minus the nth speed of the wall times the surface area of the body. Okay. And that's a horrible looking T. It looks more like a theta. Beautiful. Much better. Okay. Now, we're going to make the same approximations as before, because we're only trying to get some back of the envelope estimates about how this changes for a slender body versus a blunt body. And so since I'm making the same approximations, what I get then is that the amount of heat going into my body over time, not my body in general, but just these aerodynamic bodies going through the space, please remember that, is equal to 1/2 times density infinity V infinity cubed times cross-sectional area times my overall integrated Stanton number. Cool. Okay. Now, one cool thing we're going to learn right off the bat is that our overall integrated Stanton number and our skin friction number, well, they are pretty well approximated by this ratio of 1/2. How we get that? There is, some more stuff we're going to find out about later called Prandtl numbers and other things we can go into. We're not talking about that right now. Just know that we were taking that and saying, okay, it's going to help us out here. And this helps us get in a relationship between the two. So that's good, because what I can do then is I can get rid of my overall integrated Stanton number and put it in terms of skin friction coefficients, something that I've dealt with in the past. So if I do that, I can continue to develop this equation and see how things change. Not too much has changed yet. When I have 1/4 rho infinity V infinity cubed times the surface area times my skin friction coefficient. That's all coming from here. Okay, now let's see if we can get our coefficient of drag, because that's going to be what we bring in next. So I know that this body that's going through space, whatever it is, it's feeling drag. And so my force it's feeling is equal to drag, which is going to be equal to negative m dv infinity dt. So the change, mass times acceleration here. Pretty simple stuff. I can also rearrange that if I want to, and I can say, okay, well then my change in velocity with time is equal to negative of my drag over my mass, which would also be equal to 1/2, 1/2m, rho infinity v infinity squared, times the cross-sectional area times the coefficient of drag. Okay, and I want to make sure that this is completely clear that that's 1/2m, not 1/2 times m. There we are. Perfect. Now, we don't have a dv infinity dt in here. It's not in there. but we can make it come. How do we make it there? I'll show you. So we know that dq dt, so we have, and I can say that that's equal to, let's make sure I do this right because I always want to do it wrong, dv infinity dt dq dv infinity. There we go. Just chain roll. I'm chain rolling it out, and so I can do that. And so this helps me out. So using this chain roll, I can now bring in my coefficient of drag. And what I'll get then is, let me see, I'm gonna, actually I'll do the whole steps. So if I want to do that, let me first figure out what dq dv infinity would be. So first let's do that. Sorry, change my mind about how I want to go about this. Sue me. Don't sue me, please. That'd be terrible. I would not like that. Okay, so I'll put it in this way. dq dt is equal to dq infinity dv infinity, there we go, times the stuff that I had before. Yeah, this guy right here. So 1 over 2m rho infinity v infinity squared s times my coefficient of drag. And the dq dt is also equal to what I had earlier, which is simply 1/4 times rho infinity v infinity cubed times the area and times the coefficient of friction. So you see you've got coefficient of drag on one side and coefficient of friction on the other. And so I can then say that dq dv infinity is equal to negative 1/2 times v infinity times the ratio of my coefficient of friction to my coefficient of drag. And if I then integrated that, I can get that my total heat being transferred into my body is equal to 1/2 times my coefficient of friction over my coefficient of drag times mass times my velocity at the edge squared. Beautiful. Okay. So this is helpful. But we should realize that only one thing changes based on the shape of my body. This is the only value that changes based on the shape of my body. So let's look at slender versus blunt and see what happens then. So for a slender body, something like this, and I have a blunt body over here. Well, what do I see? Well, my slender body has a large CF and a small CD. It doesn't have much of a profile, and so it doesn't have much wave drag. It does have a lot of skin friction drag though. In the second case, for a blunt body, I have a very small skin friction drag and a much comparatively large pressure drag. So if that's the case, for a blunt body, CF over CD is much, much less than 1. And for a slender body, CF over CD is large. So, if we go back to our heating equation, we can see that the blunt body has less heating. And this is why we care. I do not want heat going into the surface of my body. If I have that happen, well, I'm going to have heat no matter what, but if I have too much of it, it's going to melt, or the people inside are going to get cooked. And I don't want that to happen. I want them to survive. So, hopefully this helps you. And let's see. We'll stop it for there right now.